Swayam Prabha. Digital India. Educated India.
We have found the response of an RC circuit, or in general a first order circuit, to an exponential input. Now, the solution we got was general except for one particular case when SCR plus 1 was equal to 0, that is in our usual notation, meaning when the exciting exponential has the same time constant as the natural response of our first order system, the solution we got was not defined because the denominator went off to 0. So, what we are going to do is to take the appropriate limit and see what comes out. Okay. Vc, let us say we are looking for the response of Vc. Now, this could be anything else. We could be looking for the response of Vr or the current through the loop. Okay. Now, we know that the response of a first order circuit, of which this RC circuit is an example, this is okay. This is the force response and this is the natural response. Okay. Now, when S equals minus 1 by CR, which means that the exciting source is Vp exponential minus t by Rc. That is, it is an exponential which is the same as the natural response of our circuit. We see that this denominator here goes to 0, so we can't use this expression as is. Okay. So, we will examine this further. So, we know that in general this constant here is determined from initial conditions. Okay. So, to do that, what we have to do is, let us say the initial voltage on the capacitor is Vc of 0. Of course, we take 0 plus. This will be equal to Vp exponential S times 0, that is just 0 divided by 1 plus SCR plus V naught exponential minus 0 by Rc. So, this is also 0. Okay. So, we know that this V naught, this comes out to be, by solving this, we get Vc of 0 plus minus Vp by 1 plus S C R, okay, where this is the initial voltage on the capacitor. Okay. So, that is what this constant V naught has to be. So, if I use that to complete the expression here, okay, what will I get? Vc of t equals, I will have a Vp by 1 plus SCR there and a Vp by 1 plus SCR multiplying that one. So, Vp by 1 plus SCR times exponential St minus exponential minus t by RC, okay, plus Vc of 0 plus, okay. So again, this is still undefined for SCR plus 1 equals 0. So to overcome this difficulty, what we will do is to take the limit of SCR plus 1 going towards 0. So first of all, let me define SCR plus 1 to be some delta. Okay, it just turns out to be easier to do it this way. You don't have to do it like this, of course. Then this means that S is delta minus 1 divided by CR. Okay, so this expression becomes Vp divided by delta times exponential St, which is this delta minus 1 by Cr. So that will be exponential delta minus 1 by Cr times T minus exponential minus T by Rc plus Vc of 0 plus, and this can be rewritten as, you observe that this is nothing but exponential delta T by Rc times exponential minus T by Rc. Okay. So, I will take this exponential minus T by Rc, which is common to this term and that term outside. So, I will have this whole thing to be equal to Vp exponential minus T by Rc, okay, and I have exponential delta T by Rc minus 1 divided by delta plus Vc of 0 plus, and I have to take the limit of this as delta tends to 0. When delta tends to 0, SCR plus 1 tends to 0 or S tends to minus 1 by Cr. In this form, it turns out quite easy to do that. Okay. I am sure you are probably already familiar with this limit. You may have taken it in some other basic class when you learnt about limits and so on, but I will do it here. So, one of the ways to do it is to expand this exponential in a power series. So, we get 1 plus delta T by Rc plus delta square T square by 2 times R square C square plus higher order terms involving delta T cube, delta T to the 4 and so on, and finally, we have minus 1 coming from there. The whole thing is divided by delta. So, now this 1 just cancels off with this minus 1, and this delta here cancels with this. So, this term alone is left out without any deltas, whereas all the others will still have deltas. This delta square becomes delta, the next delta cube becomes delta square and so on. So, when you take the limit delta going to 0, so all these terms which had delta with a power more than 1 will go to 0. We will be left with only this T by Rc. Okay. The limit as SCR plus 1 goes to 0 of Vc of t, which is really Vp by 1 plus SCR exponential St minus exponential minus T by Rc plus Vc of 0 plus exponential minus T by Rc. This whole thing will be equal to Vp times T by Rc exponential minus T by Rc plus Vc of 0 plus exponential minus T by Rc. Okay. So, the total response equals Vp times T by Rc exponential minus T by Rc plus Vc of 0 plus exponential minus T by Rc. Okay. This is the force response, and this is the natural response. Okay. So, one thing you can observe is that the coefficient here of the force response is V p times T by R c. Okay. Remember, the input was V p exponential minus T by R c, and it gets multiplied by T by R c. And if you observe this multiplying factor, or the gain, so to speak, of the forced response, this goes to infinity as t goes to infinity. Okay. Now, this is a general feature that you will see, that if you excite a system with its own natural response, then it will have an infinite gain for that input, right. A system will have an infinite gain for its own natural response. Now, this will be even more evident when we have sinusoidal inputs and a circuit with a sinusoidal natural response. Okay. Then you can see what is known as resonance. Now, this is also a type of resonance, but the point is here, the total thing will not go to infinity. Although this multiplying factor goes to infinity, this exponential falls off to 0 much faster than this T by R c goes up to infinity. So, the entire response still goes to 0. Okay. So, this phenomenon is of resonance is not very evident here, but the point is that the gain for the input, when the input equals the natural response, is very large. As t goes to infinity, the gain also goes to infinity. Okay. Now, remember, for some other input, when S was not equal to minus 1 by R c, this gain, instead of this, it was 1 by 1 plus S C R. Okay. Now, you can if you just substitute SCR equal to minus 1 here, you will get infinity, but you see that in the actual response you have T by R c, and as t goes to infinity, this number also goes to infinity, but the entire response goes to 0. Okay. So, in general, the total response of a first order circuit to its own natural response is this which can also be written as V p times T by R c plus V c of 0 times exponential minus T by R c. Okay. This is for a differential equation, which is okay. You can also evaluate this for other differential equations where different terms are scaled differently. Okay. The important thing is here, let us say the coefficient of V c is 1, then this coefficient is the time constant, and the time constant of this exponential is exactly the same. Okay. So, when these two are the same, okay, when the time constant of the differential equation is the same as the time constant of the exponential on the right hand side, you will get this solution. Now, some other terms could be scaled. Instead of this V p, you could get something else here, and that will appear in this position. Okay. Now, this is useful in itself to understand, and also Later, when we discuss second order systems, a particular case of second order systems reduces to this case where a first order system is being driven by an exponential which is equal to its natural response. Okay. So, this is quite an interesting result and worthwhile remembering, as well as figuring out how to derive it from the other general expression. Okay.